Hello, this is Nefi Varela, and in this video I'm gonna talk about our hearing. And everything's gonna start here in our outer ear. So we're gonna have a sound wave that is gonna go to the inside of our ear. And in our outer ear, we're gonna have these structures named eardrum. So eardrum is gonna work as a drum. It's gonna be hit, chum, and it's gonna vibrate. Chum is gonna vibrate. This is gonna help us to amplify this wave. Okay. In the middle ear, we're gonna have this called ossicles, the malleus, incus, and stapes. And again, it's gonna help us to amplify that signal and take it to this oval window that is gonna be the entrance for the cochlea, that is part of our inner ear. Okay. Within the cochlea, this wavelength is going to be converted to a liquid wave, okay? Because we have two type of liquids named endolymph and perilymph in our cochlea, okay? We're going to have this fluid, and within the cochlea also we're going to have this called basilar membrane that is going to help us to achieve something named resonance. What's resonance and how it works? So let's suppose that this is like a piano, okay? This is like a piano. And a piano on a specific key is gonna produce a specific sound. If we go like from one direction to the other, we're gonna see like higher sounds and lower sounds. Okay, so it's gonna be pretty much the same. We're gonna have a high region and a low frequency region. Okay, so the wavelength is gonna trigger in a specific part where it's gonna vibrate. This is gonna vibrate, and it's gonna send a specific signal to a specific part of our brain to be translated into a sound. Now, within the cochlea, we're gonna have this scala vestibula, scala media, and scala tympani. Okay. Within the scala media, we're gonna have this structure named organ of corti, formed by a tectonic membrane and this named cilia and our basilar membrane. So the cilia is going to be surrounded by two membranes as a sandwich. Okay, so we're going to have this sound coming from the perilymph, and this is going to make this membrane to vibrate. And within our cilia, we're going to have these hair structures named stereocilia. Okay, so I'm going to represent it as a hand. As you can see, it looks pretty much the same. So here we have this membrane that is going to vibrate. And we have this other one. Okay, so when it vibrates, it's going to go up and to a side, up to a side, up to a side. And as you can see, my fingers are moving. This is what I'm doing. Sure. Can you see? And within our cilia, we're going to have these mechanically gated calcium, potassium channels that are going to open with this change of movement. Okay. Pretty cool. So what's going to happen? We're going to take potassium. We have a concentration of 150 millimoles per liter. And here again, 150 millimoles per liter. So we're going to take some potassium to the inside of the cilia. Okay. And this is going to help us to depolarize this structure. Okay. We have a voltage gated calcium channel. We already know how they work. So the polarization is going to help us to make this door open, and calcium is going to get into our cell. We have SNOR proteins, exocytosis, glutamate. It's going to help us to reach an IPSP. And finally, it's going to be sent to our brain, this signal. Okay. So this is pretty much how it's going to work. This is going to be, the polarization is going to happen passively. And again, it's worth to mention that we have this sodium-potassium pump, these channels here, and this potassium leak channel. So potassium is going to go from here to here, then from here to here. And then it's going to be taken to this part, to the perilymph, where it can be reused in the endolymph to repeat that process. So I'm seeing that we have a high concentration of potassium here, and we're going to have a low concentration in the perilymph. We're going to have a higher concentration of sodium, okay? High, high. So, as you know, we're going to need an active process to take potassium inside that it can be used. So here's everything's where it's gonna start. So potassium to the endolymph. How are we gonna fill this endolymph with potassium? Everything starts with some sodium potassium pumps, and this special protein that is gonna take sodium, potassium, and two chlorines to the inside. So we can see we're gonna have an accumulation of a concentration of potassium here. Now a potassium leak channel. Driving force is gonna help us to take potassium here. Now we're gonna have this structure again. Sodium, potassium, chlorine is gonna be taken here, and again, a potassium leak channel. So as you can see, it's gonna be accumulating high, higher, more high, even higher. And at the end, we're gonna reach this 150 millimoles per liter that we have here in our endolymph. Okay, driving forces are gonna help us in this process. It's worth to mention that we have 40 millivolts that go to our cell and 80 millivolts to cross to our cell. Okay, so this is how it's gonna work. This is gonna be a passive process, but taking potassium to the endolymph is gonna be an active process that is gonna be facilitated by these special proteins for these three ions: sodium, potassium, and chlorine. Sodium potassium pump and potassium leak channels to help us to reach this concentration. So this is how it's gonna work. This is how we're gonna reach this action potential. Everything starts here, and I hope you liked it. And this is Hearing. Nefi Varela.